Okay. The next presentation will be given by Gabriela Almeida from Institute of Chemistry, Unicamp.
Good morning. I am Gabriela Almeida, a master student, and my project is microfluidic devices combining dielectrophoresis trapping and SERS detection. Dielectrophoresis, or DIP, it's an electrocinetic motion that occurs in a non-uniform electrical field and can transport charge and neutral species. So the big difference is DIP can separate neutral species. The separation DIP is based on the size and the shape of the particles and some intrinsic properties from the medium and the particles. Most of DIP studies use electrodes and apply AC current to make the non-uniform electrical field necessary to DIP. But in this work, we used an alternative, insulator spillers inside the channel, and we apply DC current. But if we are using DC current, how is it possible to have the non-uniform electrical field? The insulator spillers inside the channel will deform the field when we apply a DC current. So we have a potential gradient. We have the non-uniform electrical field necessary to DIP. The end of this work is the concentration of gold nanoparticles using DIP in a microfluidic device for intensification of Raman signal by SERS effect. Here we have the template that we use to make our micro device. It's possible to see the insulator spillers that will deform the field. We use PDMS to make our micro device, and the base was glass in the first part of this project. In the second part, when we couple the system with Raman, we use silicon because glass have a high intensity fluorescence in Raman. First, we studied the DIP system using polystyrene particles at different pH. We use pH 4, 5, 6, and 7. Then, we studied the behavior of gold nanoparticles in the system. Here, we have the setup that we use to trapping the polystyrene particles. We have the micro device connected at 2 electrodes and a high voltage source, and the camera to monitor the system. The real setup that we use in the lab, the high voltage source, and the micro device. Here we have the polystyrene at pH 4, and it's possible to see the electroosmotic flow when we apply the field. Increase the potential. We have the concentration of these particles like lines. Then, in the high potentials, we have the trapping of these particles like a cloud of particles trapped near the pillars. So here we have a cloud of polystyrene particles trapped. Change the pH, we have a different behavior during the trapping. In a place of a cloud of particles, now we have clusters of polystyrene particles trapped near the pillars. So here we have the clusters of polystyrene particles. During the study of the DIP system, we observed that you have different behaviors depending on the applied potential. First, we have the electroosmotic flow when we apply the lower potential. Because DIP first is from second order in relation to the field. So, when we apply the lower potential, we have the DIP first isn't important in the system. So, we have the other electrocinetic forces in the system. We have the electroosmotic flow that will introduce the particles in the channel. Increase the potential, the DIP first is equal to the other electrocinetic forces in the system. So we have the concentration of these particles like lines, is the string regime. Last, when we have the high potential, the DIP first is the most important force in the system. So you have the trapping of the particles here. The trapping depends on the pH. So at pH 4 and 5, the trapping occurs like a cloud of particles trapped. And pH 6 and 7 occur like clusters. So here in pH 5, we have the cloud of polystyrene particles. and pH6, the clusters of polystyrene particles. So we studied the system with the gold nanoparticles, and here we have another video. It's possible to see, we will measure here a cluster of gold nanoparticles, here. Then, pass the time, increase the applied potential. Other clusters we will measure in the system too. So here we have other clusters, here. The last one, here. Different of polystyrene particle, it's impossible to see the electrosmotic flow and the stream regime because the size of the nanoparticles, they are so small. But when the DIP force is acting in the system, they create agglomerates that get big, and it's possible to see in the system. So we decided to couple the system with HAMA to study if it's possible to control the size effect using DIP, control the size of the gold nanoparticles clusters. Here we have the setup, DIP, coupled to HAMA. We have the micro device and the HAMA. The real setup, we have the high voltage source, the HAMA, the micro device, and the laser of HAMA. We use the crystal violet because don't have HAMA signal without SARS effect, so it's good to measure the SARS effect. First, we have a signal, but it's from the silicon that we use like base for our micro device. Apply the potential, we have the SARS effect. We have the signal from crystal violet. Increase the potential, we have the increase in the SARS effect too. In blue, we have the high intensity SARS effect, then we have a decrease in the signal. But what's happening here? When we apply the potential in the system, the DIP force is acting in the nanoparticles, creating clusters. When we agglomerate the gold nanoparticles, we are creating hotspots, regions that have high intensity field. So we have the SARS effect, that is the intensification of HAMA signal. How much more hotspots we have, more is the intensification by SARS effect, but we have a limited. When we have a big clusters, we have more hotspots, but some hotspots will be inside of these clusters, will be blind inside of this cluster. So they are not available to interact with the violet crystal. Because of this, when we have a big cluster, we have more hotspots, but less hotspots available to the SARS effect. We have a decrease in the signal. And what we see here, we have an increase in the signal until a limit, then a decrease in the signal. So to conclude, we have demonstrated that it's possible to control the SARS effect using DIP. I want to say thank you to Maria Helena Piazzetta and Angelo Gobi from LN Nano, all the group of electrophoresis and microsystem at Unicamp, CNPq, FAPESP. Thank you very much.
We have time for some questions.
Thank you very much for a very nice and lively presentation. I was wondering, can you also use it the opposite way? So let's say you can characterize clusters by looking at the SARS effect. If they are too big, the signal goes down. So you can characterize the size of the cluster. Is that a possibility? I mean, turn it around. Now you say, okay, I want a cluster. If the cluster is too big, the signal is going down.
Yes.
But you can also use the SARS technique to characterize the cluster. You have different clusters. You look at the SARS effect, and you can say how big is it.
I don't know the size of the big cluster, but I know it's around 1 micron.
1 micron.
1
okay.
micron.
Okay.
And if it's more than 1 micron, we have the decrease in the HAMA signal.
How big are the particles? The gold nanoparticles?
The gold nanoparticles, these gold nanoparticles are around 20 nanometers.
20, okay. Thank you very much.
Question? Gabriela, he asked about you characterize the size of the cluster by measuring this decreasing of the Raman signal.
No, because the first part, when we see the clusters nanoparticles, we use a different system. When we are in the HAMA, we can't get the imaging during the HAMA system. We only can see the size of the clusters when we are in the lab with a camera. In HAMA, it's impossible.
Okay. Questions? More questions? No questions? Okay. So let's thank again Gabriela for the presentation. Okay, the last presentation of this morning will be given by Hawari Cobas Gomes from IPT, São Paulo.
Well, good afternoon. Almost, huh? Good afternoon. I was hoping Gabriela. What is it, Gabriela? I was hoping Gabriela to assist me with my English, but she decided to speak in English, and I will have to try to speak in English also. Well, let's go. First of all, thanks to all of you for being here attending our presentation. Thanks for the organizing committee for allowing us to show you part of the work we have developed in the last year. So what we bring here today to you is an updated device related with the last year. The last year we presented to you a device which was intended to generate nanoparticles by nanoprecipitation using a 3D flow focalization device. At this time, we will modify this device in order to just not to generate nanoparticles, but also to perform a partial liquid-to-liquid solvent extraction. This is the top. This is the topic we will have in the presentation. We will boost always. Mas aqui está bem, Ah, tá. Mas que coisa que tem embaixo? Agora sim. We will start talking previously about the previous work we presented here the last year. Then we will speak about the liquid-to-liquid extraction and some simulation we had done with 3D hydrodynamic focalization. And then we will present to you the device, the simulation we had done, and the results. So all the work was done at the IPT and in the microfabrication labs. There we have all the technological equipment in order to develop all the LTCC process. That is the substrate we had used for the device. There we have also a micromilling facility, and we are working now on in order to put into work our clean room facility. So the last year we had presented to you this device that is intended to generate nanoparticles. It is composed by 4 anti-solvent input and a dissolved material input. Thanks to the input configuration, we ensures a 3D flow focalization inside the nanoprecipitation channels. So we realized that by simulation, we used console for simulation, sir. So we realized that we were able to generate nanoparticles, and those nanoparticles were flowing through the device in the middle of the nanoprecipitation channels. So we were working with pharmaceutical active compounds. In this case, hydrocortisone acetate. So when we are working with pharmaceutical compounds, we need to completely extract the solvent present in the samples. So we think, why not to perform in the same device the nanoparticles generation and also the partial solvent extraction. And that's what we, that was the present we are showing to you today. So we also advanced in order to try to determine by simulation the region in which we are generating the nanoparticles. So we saw that for a flow rate ratio of 10, we generate the nanoparticle just in the middle of the nanoprecipitation channels. Once those nanoparticles were generated, they were flowing through the device until reach the device outputs. So here at the middle of the device output, we should have the generated nanoparticles. And that's the principle that we will use in order to extract the nanoparticles and also to reduce the solvent content in the sample at the sample output. So this work was presented in the Journal of Ceramic Science and Technology the last year. So the idea for the liquid-to-liquid extraction was to use a microfluidic device and the diffusion in order to, for example, this is commonly seen in the literature, an A-shaped device. In here, is flowing a fluid with a high solvent content. And here, for example, could be flowing water. Thanks to diffusion, we will have a mass transport from the high solvent content fluid to the lower solvent content fluid. So hence, at the output, we are taking out partially the solvent by these outputs. So we are reducing the solvent content at this output. That's the idea we are using in our device. The actual device uses a 3D flow focalization that was also used in order to improve the solvent diffusion. So the idea was, why not to put a same channel configuration at the device output, and then we could focalize we get the 3D flow focalization, and while we focalize the fluid, we are generating the nanoparticles. We are diffusing the solvent from the middle fluid to the surrounding water, and here at the output, we are collecting the samples, and by the discard outputs, there is flowing out from the device the water plus solvent, and this is the idea in our device. So it's selectively use an output channel arrangement in order to extract the solvent present in the sample. But the device we presented to you the last year had a problem. That is because we have a different channel configuration at its input, we have different hydraulic resistance, and hence the device is not fully balanced. As a result, we have a focalizing stream that will be changing its shapes gradually until we obtain something like this for the flow rate ratio of 20. This is not interesting for us because we need the focalizing stream to be centered in the middle of the channel in order to extract that fluid at the output. To solve this situation, we updated our device to a device like this. We changed the input configuration and we put this output configuration. With this input configuration, we have an aqueous phase that we split into 4 channels, all of them with the same hydraulic resistance. This ensures for us to have a fluid force action that acts equally in the horizontal and in the vertical directions. And here at the output, we have this extraction channel that is centered, related to the main channel cross section. So the focalized fluid and particles will flow through this hole, to this channel, and the discard fluid will flow through the discard output channels. This is the device we use. Simulation done. With the simulation, we saw that for a flow rate ratio of 10, we ensure that our focalized stream remains almost without changing its shapes. So we will be able to collect here at the output this fluid. So in order to simulate our system, we used 2 project variables: the main channel length and the focalized stream output channel hydraulic diameter. This one. We use these values in order to make the simulations. We saw that the diffusion stage was modified with the main channel length. For example, with a main channel of 6.5 millimeter, we obtain a diffusion stage of almost 85%. Ideally, we will need a diffusion stage in the order of 100%. That means that we have the solvent completely diffused at the cross-channel output, and we can extract part of that solvent. For example, here, we have a high solvent content in the middle. We remember here, in the middle, we have the output channel. So if we collect this sample, we will have a sample with high solvent content. So we need to reduce that solvent content, and for that we need a higher diffusion stage. We use a factorial experimental approach in order to realize how those variables influence the extraction efficiency. The flow rate ratio, the total flow rate, the main channel length, and the output hydraulic diameter. And we saw that these 2 variables are significant for the extraction efficiency. So the output hydraulic diameter is inversely proportional to the extraction efficiency, and the main channel length is directly proportional to the extraction efficiency. So a simulation predicts extraction efficiency in the order of 80% for the longest main channel and the smallest output hydraulic diameter. This is a microfluidic device we construct in LTCC using a traditional LTCC process. This is the inputs, the organic phase, the aqueous phase, the organic phase inputs, and the sample output and discard outputs. So we use gas chromatography in order to calculate the extraction efficiency. we have two outputs. One output is the sample output, and the other one is a discard output. So with the gas chromatograph, we obtain the acetone concentration. We use water and acetone in order to validate our device. With we obtained the acetone concentration. With that concentration, we obtain the acetone volume on each one of the outputs, and from hence we calculate the extraction efficiency. The experimental layout we use is composed by two stream pumps. Here is our device. We have to put these tools in order to, because it's a gambiarra, más o menos, just to maintain on its right position. That's something. That's the idea. So we use another factorial experimental approach in order to, with that device, see how the extraction efficiency is